Wei-Ting Chen. And Professor Wei-Ting would like to share about the topic, the organized convection playing a central role in changes in weather and climate. Let's welcome Professor Wei-Ting.
Okay, thank you. I want to thank Professor Guo and Junyan for organizing this workshop, and I really enjoyed the opportunity to talk to James, and especially knowing that we have a lot of common interest in research topics and methodology, actually. And my topic today is very big, I know, and actually that's probably something I know I will not finish even with my whole career life. But I think it's a topic that worth spending the whole career on. So and today the main results I'm going to show is done by two key members in my research group, Peng Ren and Shaoyu. So Shaoyu is attending another conference in Yokohama right now, so he cannot make it here. Otherwise, I think he will enjoy the talk by James. And also I have been collaborating with Jianming and Junyan in along the line of this research topic. So I want to also acknowledge them. Okay, so I know I don't need to preach how important organized convection is to the weather and climate systems in this room. But here I want to emphasize that when I mention organized convections, I don't really impose an subjective scale or size to it. Although I know most of the common definition is for the mesoscale, but really when you really look at the whole spectrum of the convective systems, you know the variation among these organized convections can range in a broader range. So, however, I think there are many observational and also modeling studies revealing how important the organized deep convections to our present weather and also in climate change. So this is an example. This is a satellite tracked climatology recently, and they revealed the occurrence frequency of these mesoscale convective systems in the world, and you can easily see they are a lot of these systems occurs in the tropics and the monsoon regions and also the ITCZ. And they compute the rainfall directly associated with these MCS systems, and then you can see there's over 50% of contribution to total rainfall by these systems in the tropics to the extratropics. And also there are observational studies. This is kind of earlier studies, but they also use the satellite data to decompose the trend in precipitation over this time period. And they then also delinearize how much of this is contributed by the changes in organized deep convection frequencies. And you can see just by the spatial maps that the spatial distribution of the precipitation trend is nicely correlated with the changes contributed by their frequency. Okay, so we expect that, so we know that the systems, they play a central role in producing extreme weather events, and also we care about how they are going to respond to the future climate change. And this is one earlier study done by Peng Ren, and our idea is actually trying to reveal how variable the morphologies can be for these organized form of convections. So we use hierarchical clustering. So that's probably the simplest objective classification scheme for machine learning. You can define it that way. We use it to classify over about millions of cloud objects observed by CloudSat over the Asian, Australian monsoon regions. And we identified 5 distinct regimes. And they have difference in their horizontal spans or in their cloud top developments or in the internal structures of the radar reflectivity height. So I want to point to your attention is this one because they are I would say, the most horizontally extended type of convections, at least in these AN regions. And so this is 100-kilometer scale here. So these guys, they're over thousands of horizontal expansion. And you can see they have multiple convective cells internally. And interestingly, if we do a statistics for these different regimes and for their outgoing long-wave radiation, and also their precipitation spectrum, we can see this type is the most shows the most impacts in outgoing radiation, and also has the highest probability for extreme rainfalls. And then if we plot the occurrence frequency of this type along with the change in the monsoon circulation and the average rainfall in the Hofmuller diagram here. So this is latitudes in the y-axis and from January to December. So the circulation and the rainfall composite showing this clear onset of Asian Australian monsoon. And this shading, blue shading, is the occurrence of this most intense, expensive systems. You can see they are right at the core of the rain season and follow the change of circulation very nicely. So these guys plays a central role in contributing to the major rainfalls in Asian monsoon.
So you say when you mean coastal intense, you really mean near the coast?
The name comes from when we also did a spatial map for their occurrence, and they show hotspots near the coastal regions in this in the AAN regions. And while the last three, they are more like land type. So these are probably more land diurnal cycle systems. Yes, and these two more organized form are coastal.
Are they thinking about what about the organization during the monsoon trough?
In the monsoon trough, yeah, I should say, yeah.
Is that the monsoon or is not the monsoon? In this environment.
Yes. Yeah. Okay. Thank you.
Sorry.
So no. Yeah, we can discuss later because originally I focused more on the Asian Australian monsoon side of this part, but in the later part of my talk, I will shift to the Northwest Pacific, and maybe there we will start to think about to link to the monsoon trough problems. Yes. So I love satellite observations for the convection, especially the advancements of this retrieval algorithm and the sensors have enabled us to really see the internal structures. CloudSat give us the vertical structures, and here the trim and the other microwave sensors can really give us the horizontal structures of these organized convections. And also there are advancements in the simulation as well. So on the right-hand side here, I'm showing a hindcast simulation from the 3.5 kilometer NICOM global cloud resolving models. And here we plot the snapshots or an animation of convections. So with an experienced eyes, and I believe everyone here is an expert in mesoscale convections, you can readily see that the modeled convections, there's texture or their structures doesn't look right? They are more scattered and they don't really form this solid aggregates. Yeah. So it's when we go to the scale of cloud resolving model, everyone was maybe originally happy saying, oh, okay, now we don't need to parameterize that much process, and we can let the dynamics and to be explicitly simulated. But now you seem to have too much degree of freedoms to let everything interact. And then the organization of the real world is, of course, pointing to specific types of morphology or structures. Of course, this may change when the environment changes. But the model, given the similar environments, but the model convections can be very diverse in their structures. And this, you can see it's challenging, but also I think it opens up a lot of opportunities to really give us to advance in what are the key processes behind the organization processes of the convective systems. Okay. So my research interest, and also with collaboration with Jianming, is to really look at this upscale phenomenon associated with the organized convections. So we are curious on what controls the organization when for the smaller, more isolated convections to be merged or to grow into more coherent structures so that it can sustain longer and maybe in a structure that it can kind of receive constant energy supplies to itself and also produce more extreme rainfalls. And also there's another line of research that many people interested in mesoscale convective system is to look at the environmental controls. So there are numerous studies looking at how tropical waves or intraseasonal variabilities or the monsoon moisture transport, for example, decide the occurrence for these organized systems. But also, so the idea is from the small scale to organized to the mesoscale, or the environments can really give us some kind of mechanism or predictabilities for the occurrence of extreme rainfall. But on the other hand, we know that in the convection aggregation studies, or when you average the atmosphere over a large enough or long enough time period, you start to see these coherent structures of convection and circulation. So the different types of clouds will nicely line up with the distribution of moistures and large-scale motion. And the question is on which spatial scale or time scale can we really see or observe the upscale effects of these organized systems. So that seemed to bring the convection aggregation studies from the more idealized modeling work to the real world. Can we really see the real world example of convection aggregation? And that's also the interest of our questions. And we think this is important for understand future climate, because this convection circulation coupling can really redistribute the energy, decide the spatial structures of the large-scale circulations, and so that governs the regional to global energy balance. And now we have a myriad of tools, numerical modeling tools, to study this series of problems. So for the more small-scale, convective scales problems, we utilize a lot of large data simulation, cloud-resolving models. And now we have this global cloud-resolving models that seem to cover a large spectrum of scales. But then, as I show you, they have their own bias. And also, on Tuesday, my student Ding Rong showed you that we have this super parameterized GCM, or the the MMF. They sort of assumed a scale separation between the large scale and the convective scale, but at least they give us some chance to explore how the change in convective process can feed back to the large scale. And to the other end, we have this conventional GCMs with a lot of parameterizations, but they are very good at maintaining the energy balanced way. So the question now is actually how you combine or strategically combine these different modeling tools to really cover the spectrum of issues. And also we need a lot of observations to arrive the observational baselines for these. And I think the satellites give us, at least from the large scale and now covering convective scales, but also as Professor Yang has shown today, we rely on a lot of ground radar and even to a lot of boundary layer in situ observations to really reveal the small scale convective dynamics. Okay. So the conclusion is to say that we really need a holistic approach that combines hierarchical modeling and various observational techniques to study these multi-scale problems. And since everyone has a picture of the research group, I'm inserting one of this and showing that to study this challenging problem, you really need a big group of enthusiastic young scientists. So this is also, again, the group of me and Jianming. And I want to tell you, all these young people, they can all do multiple tasks. They can do observation in the field. They can run high-resolution modeling. They can analyze satellite observations. So I think the way that the skills that they have is really helping us to look at the entire problems, combine all these different sorts of methodologies and perspectives. Okay, right. So now I'm sharing one recent work by my PhD student Shaoyu, published recently. So this is just to showcase our approach to look at how the effects of convective organization to the extreme rainfall. So here, this is animation, again, it's real observation. The blue color is the eye merge rainfall, and then the gray shading is the Himari brightness temperature. So this line is, we performed precipitation tracking algorithms to these satellite retrievals. And so this is one of the systems we track, and we outline it by purple. So you can see this guy. It has actually multiple rain cores and then merged together, and then gradually dies. And there are some yellows, small, if my computer is playing, sorry. So there are some, okay. So this is snapshots, and there are some yellow guys here. They are the precipitation systems during their track lifetime. They never experience any merging. So in this one example, if we plot the time evolution of the merged systems versus the non-mergers, this is their evolution of maximum rainfall during their life cycle. And you can see definitely the merger has a much longer lifetime and much stronger maximum rainfall. And these gray bars are how many items have been merged by these guys. So it's earlier in this in its life cycle that the merge starts. Okay.
How do you define the center?
So we assume we let the larger one merge the smaller ones. So the center is always the larger item. Yeah.
So the initial,
Yeah, initially this one, and then another smaller one merged it, and we redefine the center again. And then a smaller one will be combined again. So that's
your bigger seeds, and then how do you know which one?
So it's more a geometric average. So the yeah. Okay, so then from this observation, we can plot the spectrum of life duration for the non-mergers, the blue ones, and the mergers, the orange ones. Then you can see the mergers do have much longer lifetimes than non-mergers. And for the precipitation spectrums, also the non-mergers has much higher probabilities for stronger maximum rainfalls, and the non-mergers are much weaker. Okay, so with this, we think maybe you can use this to evaluate the global cloud models. But then we encounter this challenge, because traditionally people will start to do a moisture space analysis, start to stratify different environments and see whether the model produced the right convective systems at the right environment. So here we plot the maps So this is the results for the global, for some of the models participating in the hindcast, 40-day diamond hindcast for the intercomparisons. And on the left, we are plotting the contours are the column water vapor in ERA 5 or in the model simulations. And the shadings are the occurrence frequencies for the non-mergers. And on the right-hand side are the mergers. So I want to first point out that if you just look at the colors for the non-mergers, you will see maybe the models are doing a fairly good job. But then if you look at the distribution of the column water vapor, you start to see actually the distribution, even with just 40 days, the models, the column water vapor field in models start to evolve into very biased state compared to the observation. And then for the mergers, you see that their occurrence is in a very specific hotspots. And because of the difference in the column water vapors, the occurrence of the mergers in the models will naturally shift to where the most moist conditions. So this makes the comparisons for environment and convection very difficult in this situation because even with 40 days, the convection is already sort of modified surrounding environments and it becomes a chicken and egg problem. Okay, so our idea is, can we go to the convective organized process and answer the question the other way around? So here we are plotting the composite change in maximum precipitation for the non-mergers and the mergers along their life cycles. Okay, so the non-mergers has shorter life cycles. And the black and gray lines are the observational data set. So they are saying that these non-mergers should be weak, even in the peak time of their life, okay? But you can see a lot of models like NICOM or this IF 4 kilometers, they produce way too strong non-mergers. And for the mergers, most of the models get the idea right, like the lifetime should be elongated and also the maximum rainfall should be enhanced because of the merging. But they're sort of enhanced by different extents in this way. So we came up with this very simple matrix. So in this phase diagram, we are showing the bias in the extremeness of these non-mergers, just simply the peak values in this life cycle. So you can, and then we plot it against how much the extreme rainfall is being enhanced by merging simply the ratio of this peak to the non-merger peak in the respective data sets. So these two dots are the observations, so they sort of give us an uncertainty estimation. And we use iMerge as the reference, so everything is kind of scaled by it. And you can see on this matrix, the models are separated into 3 distinct groups. So interestingly, the models with convection parameterization actually, I forgot to say, actually, when we start do the tracking, we actually regrid all the precipitation to 15 kilometers to follow the CWGFS, which is Junyan's model. His model is the unified parameterization. So they are kind of coarse, but even with the same resolution, these cloud resolving models, they still produce way strong precipitations.
So the CWGFS model is the spectral model, right?
It's the spectral one, yes. Yeah, the dicore is the spectrum. Yeah. It's just, yeah.
I wrote it with my students.
Yes. And then Junyan added the unified parameterization. Yeah. So.
It's really so interesting.
Yeah.
IF is 9 kilometers. CWGFS.
Yeah.
It's very close to.
Yeah.
I was wondering, a quick question.
Yeah.
The merger, the non-merger, are you simply thinking about everything as controlled thermodynamically? Like the outflow merge or cold and is there any dynamics maybe?
Right now, our kind of very simplified hypothesis is maybe cold pool is playing an important role. but it's hard to say, I would say. Yeah. And also, I think the idea here is we use this, whenever it merges one time or 20 times, we call it a merger. And then the ones that never would experience merging is the non-merger. So this is kind of to me, it's a minimalist definition for storm mode, I would say. But of course, in the mergers, there are a whole varieties of internal structures and maybe in the ratio of their envols, stratiform regions. But when we start to do this statistics, we found that the difference among the models is so huge that we cannot. Maybe we should start with the simplest definition of storm modes to illustrate their difference first, and then to look at maybe the leading issues, and then later we can start to add more complexities to the definition of structure, and then that would involve maybe different kind of mechanism for organization. So yeah.
Because I'm not sure. I haven't followed this for a while, but a long time ago we discussed with Greg Poland is that in certain environment the convection may be vertical.
Yes, yes. Yes.
That may also lead to the merger.
Yes.
They're slightly different than the ideas of the. But I do not know how.
Yeah.
To
Yeah.
maybe
Okay.
that under certain environment.
Okay. And for the storm resolving models, they separate into two groups. So in the upper right, these are the models that are oversensitive to merging. So they have probably the right intensity for the non-mergers, but once it merged, the rainfall is enhanced too much compared to iMerge.
So the V3 is also referring to the one now using the CWA? Or
No.
The
No,
NSAP?
the NSAP. Yes.
Okay.
Yes.
So it's a final level.
Yes.
Because CWB now is also running at V3.
Yeah. So for these models, maybe their coupled collision is too efficient, we can say, or maybe, this is for James. Maybe they have much too strong cloud radiative effects to help it organize. Okay. And for the rest of these models, they simulate too strong, excessively strong grid-scale storms, we would say, because most of these non-mergers, they are small and kind of a generic form of convection formed by the model. So, but they are kind of 2 or 3, even 3 times stronger than the observations. So maybe the problems or the issues, maybe their dicore is too sensitive to heating or instabilities that quickly would produce too much rainfall. So this is just some speculations, but I think this metrics kind of help for us to at least separate the models into different groups, and maybe the mechanism behind their generation of extreme rainfalls are different, so that we can start to pick some of them to do some experiments by collaboration with the NICOM group. Yeah, that's the idea. So yeah.
This operational global model that in the U.S. Navy old time. I do not know about the Navy change, but in the old time model, we often very concerned about this something they call bull ice.
Bull's eyes?
Storm.
Yeah, great scale storms. Yes. Yeah. So NICOM has many of these. Yeah. Actually, you can see in the animation I show, they have a lot of these popcorns and small, pulse. Yes. Yeah. So I think the implication for these studies is that we really need accurate representation of both the large-scale moisture and the convective scale processes to get the more accurate life cycles and intensity of these organized systems, even in this very high resolution, our next generation global models. And so I think that really calls for process-based observational metrics to evaluate them, and also with the appropriate mesoscale dynamics behind the metrics. Okay.
I was curious, thinking that the largest instability should occur at a smaller scale. So it's something I forget how they call it, some kind of catastrophe. But would be maybe the stratiform may somewhat come to the rescue.
Mm.
in your
Yeah.
research.
So then the
Maybe the death
yes.
of some of the ice species.
Yeah, so I think the issue then would be how these models generate interaction between dynamics, microphysics, and radiation, and yeah.
So theories that are screen models, they also have the kind of couple structure.
You mean these three?
Yes, no, theories that have our screen model.
You mean these?
Yeah, the theory ones.
Okay, okay.
I think it's say that the resolution is kind of similar to the econ.
Uh,
And then so right now, since they try to resolve the popcorn cloud, so they have the 2D parameterization. So trying to things like not the single colors, the parameterization, or even it's because it's high resolution. So you don't do the kind of thermodynamic processing. So they're still trying to kind of do like a convection parameterization, but it's more like 2D style. And then to resolve those.
Yeah, extend it to the horizontal.
yes.
So they can try to, so you will kind of more like you do like a centralized screenshot that have the kind of a 2D, the vertical and the
Okay.
Yeah, maybe in a very ideal sense, your high resolution integration of this, right? Your spray, this is depending on the ice species. I know lots of cloud is open, but I think I'm thinking is that it's the spray and then somewhat.
Okay. Okay.
It's interesting.
So we are only halfway through. I'm sorry. But this is to entertain the other half of the room, Yanting and Minghui. So now this is also our recent work with Peng Ren. We want to examine, maybe, although it's kind of a little bit aggressive, the upscale effects of these organized convections. So we find a very interesting regions to the margin of the Northwest Pacific. They show regional scale radiative convective equilibrium. So we want to illustrate when they reach this RCE states temporally, how the relationship between the water vapor or cloud and cloud radiative effects shows a feature of convection aggregation. Hope you're convinced at the end. So the idea, actually, we need to thank Yanting because it has been a long conversation with her, and she has been using the energetic frameworks to really showcase the response of the large-scale circulations more zonally, but now we're starting to see the 2D global maps of these. The idea is when we consider long-term budgets of the dry static energy and calculate the budget of the vertically integrated DSC locally, then we can decompose it into the transport divergence term versus the net radiation and plus the latent heating and the surface sensible heat. And then the zonally averaged energy flux will clearly shows the northwest, the meridional shift of the Halley circulation and revealing the seasonal asymmetric shift of the Halley circulation. And secondly, this maps more echoes to the work by Booth and Cordes is they plot this energy flux potential and the transport divergence together on a map and contrasting the boreal winter and the boreal summer, then there's clearly the shift of the center of this DSC export from south to north and also from west to east. And that follows nicely with the shift in the major rain band of the monsoon systems that way.
This calculation is being done with the basic state. When you saw the elliptical equation, you just saw the elliptical equation
Yes.
without the basic state or with the basic state.
I think it's with the basic state, everything. Yeah.
But basically, you have a deficit, right? And you just imagine that was the energy source, so you solve for the Poisson equations.
Yes.
So that they're going to spread out.
Uh-huh.
But with the nature, you have a higher Coriolis force to the north. Right?
Uh-huh.
So that's you see the asymmetry of the curve showing there. But but if you saw in the Poisson equation, you're assuming everything was a Gaussian.
Oh.
But in the real hemisphere, because you have a basic state,
Okay.
there's a lot of your coefficient inertia, they make more resistance in
I understand.
this way and more.
But this is,
resistance
yeah,
in
yeah,
that
I
way.
think for winds, that problem will be more pronounced, but this is energy. So this is the center of energy, not the center of upward motion or,
No,
yeah.
I'm saying this is the center of energy deficit or surplus.
Yes,
And looks like the vector was showing where energy should go eventually.
yes,
But-
exactly.
But surely you're going to spread out. But to spread out, if you solving the Poisson equation, you're assuming the dependence is on the property of the media.
Yeah, that's
And-
the,
and
yeah.
I just looked at this diagram, just curious, because it looks like I see the latitude effect clear, but I
I
do
see.
not see more complicated basic flow resistance
Uh-huh.
of the energy spread.
Okay, but yeah, so the vectors is just a very simple
This is
solve
solving
for the Poisson
the
equation.
Poisson
Yes,
equation,
yes,
Poisson
yeah,
equation.
yes,
The Poisson equation assumes everything is a random,
yeah,
so they can go equal. But in reality, if you solve the Laplace equation with a certain coefficient,
mm-hmm.
then the ultimate energy, how they're going to spread, will be quite different.
Yes. The idea is really to look at the change in the transport directions in more general ways, and also their seasonal contrast. So here we found a very interesting box over here. So it's to the left of to the west, it's the North Pacific monsoon regions, and to the right, it's the subtropical northeastern Pacific subtropical high. In winter, this region is experienced mostly meridional transports but quickly in the summer, the energy transport become west to east. It's like this becomes energy transport corridors for the monsoon rain regions to the subsiding regions of the subtropical high. And so the question really comes to how this direction or the properties of the energy transport transition from the winter to the summer. So then we do a calculation, a similar calculation, but now we use a pentascale, means 5-day average, but over multiple years. Okay, so this is an animation showing the evolution of this energy transport. So this is boreal winter, and then around April to May, you start to see this quick northward propagation of the monsoon, and then the directions of this transport change to more zonal. And then it lingers. So the evolution of this energy is really reflecting the evolution of the monsoon rainfall, and we are thinking about that. The key is at the edge of this monsoon rainfall regions. It's actually the active pathways of the transports, and the efficiency of this transport may determine the response of the monsoon regions in terms of their energy balance. That's the first gut feelings when we see this animation. Maybe I should play it again. So the question is why these regions can be switch to this different energy transport conditions in such a short period of time, and what is convection play a role behind the efficiency of this change of energy redistribution. So the approach we take here is, this is our region of interest. So we plot, this is the annual cycles of the energy balance for this region. This is the red line. So you can see before penthouse 36, which is before July, it's in energy deficit state. But quickly, when we marched into July and August, September, in these 3 months, this region has reached almost a balanced state here. Maintain about 2 months, and then it becomes energy deficit again. So this is sort of the energy annual cycles for these regions. And then we calculate, because this is 20 years of climatology, so for each year we calculate for a specific penta, the percentage of these regions maintain the RCE state. So we can see this is the percentage, and over this period, or what we define as the RCE period, they can reach about 80 to 90% of RCE in different years, interannually, okay? And on the right-hand side, I'm plotting the map, and shading again is the DSE divergence, and then, but I want to point out to you are these diagonal lines and dotted lines. They are showing the frequency of wet condition versus dry conditions. So in the non-RCE period, which is we define here as a kind of a reference line, is the April to June. This region is mostly dry, but the wet region is kind of spread out. They are not concentrated spatially. But once the regional RCE was established in these 2 months, the wet regions become more kind of consolidated, and then they appear more frequently over the western part of this domain. And also you can see they overlap nicely with the rainfall or the DSE source regions. So this gives us that maybe this region is achieving this RCE states with an enhanced moisture contrast and also increased frequencies of convections. So the idea is we have identified a seasonal shift of energy flux prime meridians, and then we can examine the temporary establishment of the DSE transport at the edge of the DSE source, and we identify that the regional RCEs are achieved at specific areas and period. So this kind of a brave hypothesis is maybe this is kind of a realization of real-world convection aggregation. So the next thing is we want to carry out a series of moisture space analysis and also to examine the statistics of the organized convections to see whether they show the features of convection aggregation. So this is the column water vapor PDF for our 2 period. The green is the RCE period, and the blue is the non-RCE period. So we don't see the 2-mode column water vapor PDF in the idealized RCE simulations in the real world, but we do see a shift and broadening of the column water vapor distribution here. And then when we stratify the cloud occurrence, which are the shading identified by CloudSat, and also the mass flux contours here for the non-RCE period and RCE period, then you can clearly see that for the moist condition, the convective structures are quite different for the non-RCE period and RCE. So in the RCE, they become one deep, more continuous occurrence, and with higher top and a more clear outflow envelope here. But while in the non-RCE, it's more like a trimodal distribution of cloud tops. Yeah. And also, if you look at the dry regions, the stratiform cumulus clouds become more active and more thicker in the RCE period. And also, the mass flux are pointing to a more top-heavy updraft, and then also a stronger, much broader downdraft structures in the RCE period. And with CloudSat, we can also get the cloud radiative effects statistics along the moisture space. So this is showing I'm only showing the long wave cloud heating rate here, but we actually also compute the short wave and TOA and the bottom, a lot of things. And so I think the long wave is showing very coherent signals with the cloud layering here. And the lower left are the long wave cloud radiative heating to the atmospheric columns. So we can see that during the RCE period, the wet conditions receives more of this long wave cloud radiative heating in contrasting to the non-RCE period. So I think it's giving us a very nice quantification results for how the real world, if it's become maybe, we should not say it's we should not call it non-aggregated states. I think the real world's always kind of have some aggregated nature, but it's definitely being enhanced when the regional RC is established. And the final thing is to link it to the weather or more to the convective scale. And here we are using the TRIM precipitation system size distribution. We plot also on the moisture space again the occurrence rate for the large system, which are the red, and then the smaller systems are the blue. So if we take a ratio between the RCE to the non-RCE, we can see this is the one ratio equals to 1 line. So only the large systems are enhanced in their frequencies in the most moist conditions. And for all these dry conditions, the occurrence of the systems of all sizes are kind of suppressed. And also we can we also calculate the percentage of these large systems and for their association with tropical cyclones. This is the time evolution. So we can see during our RCE period, over 20% of these large-sized systems are actually tropical cyclones. Yeah, but in contrast to the non-RCE systems, these precipitation systems has no association with, very rarely with tropical cyclones. So we think this statistics give us qualitative results, of course, but I think they also linked together serve as an observational baseline that maybe we can use them to evaluate various global models from including storm resolvings to these MMFs or to conventional global models, because we covered from the energy balance issues to the convective scale statistics. So I think this regional RCE topic is kind of a good opportunity for us to examine the convection circulation coupling in a realistic large-scale constraint. Yeah, so the conclusion is organized convections are important, and we now have a lot of tools, including observations and modelings, to study them. And I think the internal structures definitely is the key, but also we need to include more process-based evaluation tools to really understand them. So the two works I presented today is just the starting point for us to really dig into these issues. And I think, I hope my talk can prompt everyone to think about how can we develop some process-based diagnostics for these organized convections, especially maybe we need to find a way to standardize them across models for more robust evaluations. Yeah. Okay. Thank you.
Enjoy your talk. Question is, can you elaborate a little bit about when you said, let's say 20%?
Yeah. So in our regions, we use TRIM to identify precipitation objects. And so for each object, we also check the tropical cyclone database, whether it's within, I think, a vicinity of 20 kilometers or something of a tropical cyclone, then we will attribute this precipitation event to the tropical cyclones. So yes. the large systems are the systems over 300 kilometers in horizontal size.
300 kilometers in one parental direction.
Horizontal, yes. Horizontal, yes. Yeah.
And among the sampling, so 20% is associated with TCs.
Yes.
Yeah, that's a really striking result. On your conclusion slide, you ended with the point, how can we standardize them? I guess your phase diagram from your first part is already kind of a way of doing that, which I thought was really creative. I think it kind of already came up as ideas to others, but the first thing that came to my mind, of course, was I've been thinking about from my own results, it sort of points me towards thinking that the most important or interesting question is what controls how much stratiform is produced for a given amount of convection.
Yeah.
And I wonder if that's a big discriminating factor in that phase space.
Maybe.
With the difference in models where, sort of the over aggregators, I guess, if they're producing much more ice for a given amount of convection. So more, let's say observationally and thinking about climate, I'm really interested in the question of what controls and what might change the amount of stratiform or ice more generally per unit convection. So what controls stratiform fraction, basically, but also in terms of a model hierarchy and model ensemble, I wonder if that's a big variable that could lend some insight, or I don't know what we would learn from it specifically, but I wonder if it would at least show up as a big signal between the different models, like the over aggregators, if they're producing just so much ice that then it amplifies like the sort of aggregation feedbacks.
Yes.
What do you think?
I think sometimes just looking at morphology can be misleading because, for example, the size distribution of the ice particles may be very different across the models. So maybe making the efficiency of the stratiform to produce for their radiative effects to be highly diverse. That's one of the issues. But I mean, I like your metrics linking precipitation to per unit of cloud radiation, something like that. So I think how we normalize things so that it reflects the key processes is something we really need to think about it. Otherwise, for example, some people one of the reviewers asked why don't we stratify our result based on how many times the merge occur, but we actually done some statistics and we found that the models and the observations are so mixed that we can really identify some systematic difference because if their original intensity in precipitation is already different, then the merge effects can very hard to be distinguished given how many times they merge. So I think their precipitation is just the quantities, but I think radiation in terms of energy, it's another quantity, but how to compare so that we will not be too much influenced by the absolute amount, but really revealing the process effects is something very challenging, but I think it's maybe the way out. Yeah.
I would like to give you some comment, and this is not from me,
Okay.
from House.
Okay.
He used to tell me that the tropical hot tub, the hot tub hypothesis, in fact, are more suitable for TCs. And this is also a quote from Peter Webster. Because tropical, originally John Simpson coined
design this lane. Tropical hot tower is for thick convection in the tropic. However, the lifetime for each individual cumulus cloud or cloud cluster very short. However, thinking about TC, the lifetime for TC could be longer than 1 week. So the coherent and the aggregation effect of the mass, moisture, energy transport is more suitable for RCE. So I'm very happy to see your slide.
Okay.
20%.
Okay. That part entertains you more.
Yeah.
Okay.
Wow. Cool. Peter Webster.
Okay.
Okay, interesting.
Okay. So let's move on.
Yeah, let's move on.
Thank you.
Thanks for making it in. It's a wonderful talk. Okay.
跟你换吗？对啊，跟你换。我是不是不应该帮你搬？
那滑。拜拜，感谢。好。对面会很空，你可以坐对面。
Okay.
So I won't see you tonight.
No, because I have some appointment. Tomorrow is a holiday for NTU.
Well, I wanted
这要怎么别啊？
to bring a little piece of pen.
就压下去。
你可以就把它当成是一个夹子。
哦。
那个是比方说 T 恤不好夹。
好，然后夹着。
Yeah, give me that.
对，但是你要 spray 出去的时候，
我们等魏天老师回来。
这个会被就像科技一样。那这个流场在大体上面空间的，是拿空还是算，还是拿 A 还是没有
Sharing your supervision and everything. It was really fun to
因
see
为
what
这
you're
个会
working on.
就是
And,
classical，
yeah, you can keep in touch. Yeah.
他们这个会对啊对啊。
Yeah. Are you going to the Hurricanes and Tropical Conference?
你做一个大概
April?
那个是个 2D 区的，那你要算那个，你现在算 vector 是一个
I think
2D
you're right. I think you're right. I just know it's during the semester. But yeah, it's funny like there's so many CSU connections all around.
Maybe I can introduce.
还是我去上厕所好了。
We're working on it.
啊，人都回来的话，帮我 hold 一下啊。我也先去个洗手间，洗手间一下。
they definitely dedicated to do research.
Yeah.
So you will see that.
Yeah.
Very good.
Yeah. I feel, yeah, when you travel somewhere else for research opportunities, like I felt that way in Germany, like, okay, I want to do really good, make a good impression, things like that, but
And we have this kind of joke about sometimes, for example, some university that doesn't have Chinese students for a very long time, the last students must do something wrong. And then on the opposite side, at Kaiji State, all the students benefit from kind of something like this.
Maloney was advisor?
Energy should spread all the way.
Like in say we don't have students from very long time.
Circle geometry.
Yeah, so we always bring the last students on like senior.
Wait, so even right now, there's not.
There is a but I guess because in my age, I don't know. So I went to university
In the end of the day,
and
the
come
energy
back
should flow
to
to
the
the
lab.
lab.
So
但
that's
是
years.
实际上天体
No one
那
is
是另外一件事。
That's very
但是
weird.
我们说你有你的 basic state 的时候，譬如说你在
Because every year we sort of have
energy
five.
in the end of the day 你就做到这样，那中间天体怎样？
Almost every.
可是我当你的 basic state
Now it goes
Now maybe they'll avoid
go
the
for
US.
the
Go to Germany or somewhere else.
Well, for this year, a lot of students that apply the
因为我们在
US
想这个
funding,
事情，就是
so they have to shift. Some go to Japan,
在
some
爱
go
国
to
共去，
Yeah, okay.
有一些人就
And then I will hesitate to tell them, oh, maybe you can go to US because they might not get funding.
They might not get funding, but also
那你就是特别，所以他那种 energy，
I don't really think that people are on a large scale being deported or having their visas revoked, but the threat of that is enough. You know, it's like if you're the student, that feels very threatening.
Yeah, for students, I cannot imagine if I was there. I will be very.
Yeah, that's no way to live. The government of the country that you're in feels that way about immigrants.
Imagine that I have kids at that time. Exactly. What should I do?
I get thrown in alligator. What is it? Crocodile. What's the name of it? The Florida prison. Yeah, no, there's scary stuff going on. So I sort of feel for my colleagues overseas not wanting to send their students like to the US right now. So that part's really sad, but I'll also visit outside the US as much as I can during all this time. Yeah, hopefully gets better soon. I just kind of want to go through a wormhole and appear 3 years from now and see that it got better. Because I said the other day, sometimes I'm like, all right, well, surely we must be near the end of this, right? And it's not even 1 year out of 4 years. Just like, wait, how is that possible? How is it taking? Time has slowed down with all of this craziness. We've lost some people.
Yeah, we should wait for Professor Guo. Yeah.
Please keep it within 20 minutes. Please. Last person was like 15 minutes. I checked the time.
That's why she said let's move the schedule ahead because she wants
You were
to.
thinking ahead, yeah. I could tell.
Yeah.
That's really sad.
Sorry.
She will use every last minute of the time she
That's
her style.
yeah.
So normally in a 15-minute talk, she will give like 18 minutes. So it's so typical. I'm so used to it.
I think I was guilty of that too today. But I think also it was just the thought-provoking results. Like people can't help asking questions in the middle of it. You got interrupted like maybe 10 times.
I enjoy the discussion.
Yeah.
Meaning you are all paying attention. That's good.
Okay, I think let's start. After. Let's wait for it.
Yeah. I also like your branding for your research labs. I see
Our
the
logo.
overlapping influences of branding with the logo and really nice websites and everything.
The logo was designed by our students.
Okay. It's a great idea. I spent in my first year as faculty, I probably spent like weeks like touching up a website and trying to make it look like, but probably students could have done a better job.
Now you can use ChatGPT to help you.
Right, exactly. To make the logo, Are people using that for their schematics a lot?
I think, yeah, we tried once at first, yeah.
Every schematic is done by
It's ChatGPT, yeah.
I'm trying to.
I haven't tried it.
I always got so mad at it whenever I tried.
Yeah.
It doesn't want to follow whatever I'm in my mind.
It's easier if you give them a style as a reference.
And you give them some example first.
Okay.
And then don't come on it to spelling you right. Don't do that. Just schematic and do the spelling by yourself.
Okay. Yeah, I've seen some pretty weird things from it when I've asked it to show like what a cloud should look like or something like that. But no, I haven't tried it in a while though, so it's probably gotten.
It gets
probably
a lot better.
Yeah. But yeah, you were commenting all of my Naoko's. She and I work together a lot, and she's like, "Yeah, your schematics, some elements of them all look the same because I use the same clouds, similar clouds, and I'm not going to invent new clouds. Like I put a lot of time into those little things on Inkscape."
Your clouds definitely have flat bottom. That's Jimmy's criteria.
Yeah. My criteria
If you
of
know
distinguishing
convection.
we are friends or not.
Yes, because lots of our students or many in the field will just like whenever they have like stratus clouds, it will be like half points. And then whenever they want big convection, they will just rotate it.
Yep.
Then you have these
The little the rounded bottom. Yeah. They use the PowerPoint cloud and
Stretch it.
And they're all
that
the same.
annoys Jimmy a lot.
Yeah.
So that they are not my friends.
But you have the proper clouds.
Bjorn Stevens would say that that's how you can tell the theoreticians from observationalists.
Should we go see where
it's been some very
Conjure
nice
said.
schematics though, and like conceptual models they're really impressive. And everyone's
去找人吗？还是没关系？
Conveys a nice, it helps to convey the story in a simpler way.
Should we start now? I don't know.
Maybe you can. You are the chair.
Okay. Okay, cool. Before I start, I would like to thank James taking our invitation to come out again, because we all know it's such a long trip from Oklahoma to here. Yeah, you have to take like 3 flights, right? And after you arrived, we make you full schedule after the day you arrive, after the evening you arrive. So yeah, you have 3 days full of schedules. We know it must be very tiring for you. So we hope the conversation and the talk and the discussion we have with you can make you want to come here again. So I met James at a local diner at Baltimore the first time, I think. And that was at an S meeting, and in the evening, and John texted me, "Hey, I'm meeting with a guy, James, and he's really nice. Do you want to come out and just chat with us?" And sure, of course, I would like to go. And at that meeting or in that diner, I learned that James and John were actually roommates when they were in CSU, and they studied together and as PhD students. So after that, when I came back to NTU, there was one time I attended Bofu and Hundred's group meeting. I heard them talking about they were at a meeting at CMCS, and they met a guy, James, and they were having very, very nice conversation. So I brought up this idea that, hey, how about we invite James and John to come out to Taiwan, and we can make a small workshop, and we can have a lot of great conversations. And thanks to Hongji, and he immediately agreed with that idea and supported us to arrange this whole stuff. Okay, I think that's the story I would like to tell. And this is, just want to say this is just a very small world, and we are very lucky. And I feel really lucky that we have a chance to meet with each other, to doing great research with collaborations.
Yeah, the feeling is mutual. I really appreciate the opportunity to come and visit and talk with everyone.
Okay. Now I'm going to start my talk today. I would like to introduce the SURAS. It's a unified scheme for representing deep convective storms in convection permitting simulations. In this work, I'm collaborating with John. And so, yeah, we're still having footprints from Penn State. NTUxOUxPennState, yeah, we're here. So first, I'm going to introduce some of the background why I want to develop a scheme, a convection scheme in convection permitting simulation. So here is the observation panel showing tropical rainfall has increased in the past decades. Here is from a train passive precipitation analysis, the changing trend from the past 30 years. So you'll see that there's green colors of the tropical oceans. Probably some of you might be more interested in the brown color showing the decreasing trends, but this is the increasing trends that intrigues me about the whole idea. So now we know that this is observational facts. Tropical rainfall has increased in the past 3 decades. However, observational studies also reveal that the frequency of tropical rainfall events with different intensity percentiles, they have changed in varying ways. So the panels here, the x-axis is the intensity percentile. The blue line here is another satellite retrievals of precipitation intensity. You will see that the frequency of the most intense event has increased over the probably last 4 or 5 decades, but not for the moderate rainfall intensity. And also for the light rain intensity, we have a slight increasing trend in the past decades. The orange line here on the other side shows the CME6 model means result. In the CME6 model reproduce these trends, but the magnitude you can find of the trends is muted. And also you will find the variability, meaning the variability across the CME6 model. I think they use like 19 models or something like that. The variability is even, standard deviation is even larger than the value itself. So they disagree with each other. We all know that that probably is because the parameterization, especially the cumulus parameterization in those models, probably could not deal with every types of storms very accurately. So at the time, our hope was to use explicit simulation of convection. We thought it's very crucial, or we think it's very crucial for understanding how convective storm changes under a changing environment. I think it's a very crucial or important topic. I think most of the people or most of us here are very interested in. However, when we look at the diamond winter or diamond summer simulations, they are global convection permitting models. The clouds, or showing by the brightness temperature here, even very short after their initiation, they are very, very different. So no wonder if the integration times becomes longer to 15 days, when we look at also the brightness temperature here, all the simulations here, they are very, very different compared to the observations. Of course, we know that for 15-day simulations, the predictability of those clouds probably does not exist. But if you look at the morphology or the storm modes of these systems, they're just so different. So what if, when we look at this figure, when we have enough computation resource, but the variability between these global convection permitting models of each percentile is even larger than that we're seeing between the semi-6. This is a very serious problem which really challenged our hope on these global convection permitting models to study climate change. So I'm thinking about this by investigating how individual processes modulate the response of convective storm to its changing environment. Can we really understand why the variability between global convection permitting models is large? Here's a quick example. For example, we know terminal velocity of hail is a very important parameter or variables in the model. So when we change that to a different magnitude, we know the storm morphology probably will change. But after a long time, the climate also change. So we really don't know the change of the storm morphology is caused by the change in environment or it is changed by the intrinsic dynamical process itself. So this question triggers me to develop a method for untangling the multi-scale interactions. Here's my idea. I would like to make use of the artificial scale separation of the convection in the convection permitting regime. So by the meaning of that is, I would like to separate the continuous scales of convection into two things. One is small, isolated deep object. The other part is large, grid scale, whether it is organized or not, vertical motion or deep objects. So by having this artificial separation in convection permitting regime, we may gain additional interpretability of the result we have in those long-term global convection permitting models. Also, we may examine the role of individual processes at different scales, the small scales and the large scale grid scales. So this is something like in a climatological or the environmental sense. But it may also make sense if we look at the storm evolution. So here is a kind of busy figure showing that all the global global convection permitting models, they disagree on the occurring time of MCS initiation, especially over tropical ocean. You can see these 4 panels here that represent different scenarios: MCS initiation over ocean, over land, and their mature stage over ocean and over land. And the y-axis here represents their frequency, the histogram, and the x-axis is the local time. So we can see the lower upper part, the MCS initiation over ocean, that disagree the most among all the statistics. So why does that happen? So we know for dino cycle over land, we have a strong control, and we have a strong surface flux and accumulating instability that can be a driving mechanism that trigger afternoon thunderstorms. So that's why all the models agree on the timing of the MCS initiation and also the mature phase. But for the ocean, MCS over ocean, these models, they have different treatments in turbulence and also probably microphysics. So which makes them disagree a lot on when should the scale of objects change from small scale to the grid scale, because some of them might be represented by parameterization and some of them might be represented by the grid scale vertical motion itself. So by having this idea, we may also tackle the question, is initiation of oceanic MCS affected by the change of object size? To make this idea coming true, I'm very happy to share with you this Ashura scheme. It's the single plume unified relaxed Arakawa-Shubin scheme, which means that it's a combination or the unification between single, small, isolated object with large, above grid scale, whether it's organized or not, vertical motion. So when we think about the grid scale budget for the water vapor mixing ratio here, here's an example to show what does the subgrid isolated object does to the simulation or to the equation. We know that in convection permitting regime, the grid cell may be occupied fully by the convective draft, or it can be just zero, no convective draft at all. So when the fraction is large, which means that we should have no vertical eddy transport contribution by the updraft. But the condensation or the microphysical processes in that subgrid cloud should be dominating over the microphysical tendency here. So in this scheme, there are a lot of components here. I'm not going to go through all of them. For the deep updraft part, it's a 1D buoyancy-driven conventional cloud model, and I use it with a very simplified warm-rain physics. For the single part here, I use the cellular automata scheme, and I couple it with the parent model I'm going to use, so that the decision of the single cloud type will have stochasticity and memory in it. And what is really crucial to make the unification happen is the closure for convective draft fraction, and it's developed in Arcar and Wu's paper in 2013. Okay. So to test the idea, to make sure to see what will happen if I really combine all these components, I carry out the CN1 simulations and using the convection permitting horizontal grid spacing. And I use the legacy get sounding, because in that sounding or in that environment, I can have organized convective systems, and I can see the grid scale updrafts, whether it is organized or not. I will have them both. So after introducing the idea and the components of the scheme, now I'm going to show that this is not simply just an idea. I have carried out some simulations to show this artificial separation of scale in convection permitting regime is a promising tool. So here I'm showing the vertical profile of the gas simulation, the vertical profile of eddy transport, vertical eddy transport of more static energy. So we have two lines, the black color two lines. One is the no CP, which means it's just purely the convection permitting simulation without the Shura's I develop. It's the dashed line here. And the solid line here is the vertical eddy transport in the Shura's simulations. So we know, so we can see that under the GET environment, the Shura scheme separates vertical energy transport to grid scale, the tan line or the gray line, and to the subgrid scale. To summation would be the black solid line here. And interestingly, we can see that the summation of the transport in Shura's, the solid line, is comparable to the total transport in no CP run, meaning that all the formulation and all the equation let down, they work out really well in the GET simulations. The decomposition of the energy transport really makes sense. So let's take a look in a convective systems-wise this point of view. So now I'm tracking all the convective systems in the GET simulations, and I composite them based on the life stage of those convective systems. So those life stage will be the x-axis. And we will see that, and we can see that the vertical eddy transport in the Shura's run dominates the total transport, especially in the early stage of convective systems. By meaning that, I'm showing the lower panel here. That is the ratio of subgrid transport to total transport. And we can see at the early stage in the x-axis, you can see a very dark color, meaning that all the transport is dominated by the vertical eddy transport. Okay. So what will that do to the overall storm statistics? We will see that the Shura's run has fewer but larger short-lived convective systems. The last panel shows the composites of life stages, but now I'm categorizing those convective systems based on their total duration or the length of their lifetime into 8 categories, the x-axis. The upper panel here shows the track counts, and you can see that the Shura's run, the green bar, there are fewer numbers compared to the no CP run, especially for the short-lived convective systems. But they are larger. Their maximum horizontal size displayed by those whisker plots, meaning the percentiles, like 95, 75, 50 percentiles. Okay, they are larger. The short-lived systems are larger. So let's take a look at their vertical mode. So what happened in those systems in the Shuras? Why they are fewer and larger short-lived systems? So first, and we can see that we will find that at early life stage, Shuras will already have mature subgrid deep objects with grid envelope. And it will also show the slower development of bottom-heavy grid-scale objects over here. So these figures shows the vertical velocity profiles and their average or their mean over tracks when their life stage is short. That makes sense? Then we compare the early stage and the mature stage, I mean longer than the 60 minutes. We can see in the Shuras, there are distinct deep mode and congested mode in vertical velocity in mature life stage in the Shuras. But when you see the convection permitting simulations, the dashed lines, it simply transition from a bottom-heavy profile to a top-heavy profile here. So let's take a look about what would this vertical profile or vertical modes meant to the cloud condensate profile, and in terms of their life stages. So we will see in the Shuras run, these convective systems can develop way before the buoyancy or pressure perturbation accumulated to a large enough grid scale. That's the time when convection permitting models can develop a grid scale convection. But for the Shuras run, because using some subgrid deconvective parameterization, we can already have mature phase in the early stage of those convective systems. So when we take the difference between Shuras and no-CP run in terms of cloud condensate mixing ratio, we will see there are red colors in very early life stages, from like congested cloud top all the way to the deep mode. So after the storms have developing into a mature phase, the difference becomes even more significant over levels probably near the melting level and also the envelope clouds. But there are less clouds over the levels between like 6 to 9 kilometers in the Shuras zone. So what would that do? What's the feedback to the vertical profile? So we found that it would be more stable in the Shuras run by seeing the dry static stability, the profiles of it. So no matter it's the early life stage or mature life stage, you can see that in the Shuras run, the square of this n square term, they are larger. So here's another just consistent story about the divergence profile. And it will also again shows that the Shuras run has the more convergence profile between high clouds and congestors. So between these two modes, I speculate that there's a mixture of stratiform processes, and occasionally there are transitions from congestors to deep objects. So after showing some composite of the vertical modes of those convective systems, now I'm going to jump through how do those individual events, how do those individual convective systems look like in the convection permitting models and run with the Shuras scheme. So here's the animation of a 30 dB equal top height. So in the animation, you probably can find that in the Shuras run, there are more school-like convective systems propagating throughout the domain. And not only showing the color, the grid scale 30 dB equal top height, the black shading here shows where subgrid objects develop. So you can see most of the time they're concurrent with each other. Now let's take a closer look to one individual event in the Shuras run. Okay, now I'm going to show like a Eulerian aspect of the analysis. Then I'm going to show the vertical cross-section in this 6-hour time span, and the location will be this star. And during these 6 hours, you will see a convective system, a square-like convective system, propagate from northeast to southwest. So the the panels here shows the vertical cross section. The x means the time, and the y means the y-axis means the height. And the star here shows the location or the altitude of the subgrid cloud, subgrid deep object. So this diagram, I think it summarizes all the findings I have demonstrated in the early slides. We can see at early life stage, the Shura scheme has mature subgrid deep objects interacting with the grid scale envelope. And at the early stage, we can see they are developing bottom-heavy grid scale objects. So after the bottom-heavy grid scale objects develop into a mature phase, into a very strong and deep phase, stratiforms follow those mature grid scale deep convection. And the contour here represents the cloud condensates, and of course above a certain criteria. So I hope until now I have convinced you all that Shuras is a promising tool to identify processes that modulate how convective storms change under changing environments. So to do that, in the Shuras run, we can separate the continuous scale of convection, again, into single small isolated D object by parameterization. And it unifies with the large grid scale, whether it's organized or not, vertical motion. And they are all happening in the convection permitting regime. And I will stop my presentation in this slide, and I'm very happy to have any comments or questions.
So is there a parameter testing possibility to modify the ratio of the Suras, stratiform ratio of the Suras? Is it possible to have settings so that it will change the ratio?
Yes.
Easily?
Yes.
Because I can imagine that next step will be compare with the observation, so that
That's right.
some kind of tunable parameter will be very crucial to this.
Exactly. As you can see, there are a lot of decisions to make in designing this parameterization.
Please give me one.
You mean to change the fraction of stratiform? The easiest one would be the criteria to trigger this subgrid convection.
Okay.
Yeah, I didn't mention, but I do say set a criteria for triggering.
Please give me the one you are most interested in.
Yeah.
That's the one.
Yeah.
Triggering. Okay.
Triggering. The triggering function now is a value of convective reflection. Because I think, in my opinion, it has to be larger than a certain ratio to make sense to say that is a mature deep object. Okay.
Do you see, so you showed that the Suras run is higher static stability, right? Did I have that right?
Yeah. You mean higher?
Stable,
yeah.
stable environment.
Yeah,
That's right, more stable.
Is it also warmer, like it's at a higher moist adiabat, basically?
I'm not very sure about if that's warmer, but I think it is, because when I look at the area mean of their tendency, probably in this figure, this one. So what Shuras do in the area mean sense is transporting energy from bottom to the top. So yeah, I will assume it's warmer aloft. And if you look at buoyancy, calculated by surface parcel in the average sense as well, it's more stable for the Shuras run. So that's why we will see the lower echo top height in the Shuras run.
So lower echo top height. So what about like the anvil height? Like the general anvil height? Are you able to see
Yes.
the difference?
The anvil height, I think, would be higher for the Shuras run.
Yeah, okay. So
Yeah, but the strong echo top, like the 30 dBz echo top height, that is lower.
Okay, yeah, that all fits together in my mind with shifting towards a higher moist adiabat. So it's actually like all of these signals are actually consistent with like the I mean, not as extreme as the aggregation case, but consistent with the differences you see from like a disaggregated to an aggregated RCE state. You shift towards a higher moist adiabat, and you see an elevation of anvil clouds. They actually shrink, but you show overall there's more anvil, right? Averaged over the domain.
Yes.
Yeah, I'd be curious if the anvil cloud coverage. Well, anyway, what I'm getting at is it also seems that, like if you looked at the moisture space, like in Week's results, maybe you would see a higher like discrimination between moist and dry, I guess.
Yeah.
Sort of it's more organized from that sort of a standpoint.
That's right.
Yeah.
So what I'm thinking about, one of the next steps will be some experiments like the mock Walker circulations. We can test if we change the straight form fraction, then how will the circulation respond, and how will those systems interact with circulation. Of course, we can do some homored. Yeah.
That'd be very cool.
Yeah.
I'd be really curious to see.
And for the verification, I mean to use the field campaign to verify if I can tune the Shura scheme into a more realistic setup in a certain environment. I think there will be another interesting study to do. And yeah, this is also in the plan. Yeah, I think I will try to use the orchestra data to do that research. Yeah.
Yeah, I'd be really interested in an experiment with, kind of tuned, I guess in multiple directions, the controlling that stratiform anvil, and then, but repeated sort of with and without radiative feedback, or maybe that's an additional dimension where you have kind of a spectrum, and see if the radiative feedback is kind of amplifying sensitivity to stratiform or vice versa. Also,
that's right. Yeah.
That'd be really cool.
Yeah. I'm also looking very interested in incorporating this game into VVM, into some land surface study, like convection over land, and to see if the subgrid part initiate the convection even earlier. Yeah, how will that affect the overall convection permitting circulation?
Yeah.
Yeah.
I was worried, I was concerned. I meant to ask you, so it's a double period. I'm sorry I missed your first part. It's a double period, right?
Oh, so in this simulation, yes, but this is the future work part. So in the gate is double periodically. That's right. Yeah.
Just you look at the animation.
This one?
No. This is a domain animation. Not this one.
Not this one.
The elongated.
Oh,
The elongated.
yeah.
Oh, okay.
This is
It's a beautiful animation.
I'm just wondering.
a lot of
Yeah.
artificial domain.
That's right. A lot of waves, artificial waves.
Yeah.
You know, there's a RCE MIP test too. They're using this as a setup, but I believe all the models will execute very different boundary controls on the result. So me and James and Mark, we already discussed the MIP, what will happen to the MIP about it. And I think we all agree that it will have a very, very hard time to distinguish the process, the important process in those
And also,
circulations.
You can have 6,000 and 400 kilometers, right?
That's right.
You can have a 4,000.
Yeah.
South extent.
That's right. Yeah.
Slightly different in property.
So what we are going to do is to design kind of like homoarray experiments combining with my Shura scheme, and to see how do we see the stratiform fraction affecting the whole circulation.
As a dynamic system, I'm too oversensitive density to reduce the potential.
Yeah.
And volume efficient. Yeah, very interesting.
Thank you. If no further questions or comments, I think we can move on to our last session today.
Okay, I don't need to move.
Okay, that's good.
So I take a 1 minute break.
你要 pointer 吗？
我可以用，
拿出就好了。
我可以用。
好，你想用的话就这个会亮。
可以。
然后你想要让它按钮会换页的话，就把那个 USB 插进去。
好。因为我们没有 online 吗？所以还。Sure.喂，维尼有地方去吗？那个呢？OK， 我要报告，我们这里在1个小时内结束，然后我可以去找你们。我还不确定晚上要怎么样，但我待会会先去找你们。好想你们。你们2个要去台克鲁伊莎，我待会可以去台克鲁伊莎找你们。好，拜拜。
Really strict about that, but also I travel all the time, so I take a couple Melatonin before I go to sleep, and like that, I feel like that accelerates the reset. Yeah. Helps me sleep.
One of the secret success is with the jet lag is that the first night and second night. So usually, we used to went to arriving in San Francisco at the afternoon hour, and then I drove to maybe halfway to 2.
Yeah.
And then walk the break at 10 o'clock. And then if I sleep at 9, it's cute.
Yeah.
Most of the children.
Yeah.
Like if you're not, then I know this is a sensation.
Yeah. I do feel there's like a second wave though. It's like tomorrow and the next day could be I might have like.
It would remind you.
I try to stop it. But yeah, that and I try to always move around a lot, get up, take a walk, get some fresh air, that kind of thing, and I feel like that really helps too.
Yeah, that's what I like to discussion to sit in the comfort. I understand what people are talking, but my mind is not,
Yeah.
But it's just discussion is
better.
okay.
Okay, good. Okay.
Let's welcome our last speaker for the workshop today, and Gokul Chen. Gokul Chen will talk about the BNPY model and its application in his study and with his group. And
Yeah.
Welcome, and Gokul.
Yeah. So first, thanks James to to stay with us for the stays and for all the amazing discussions. And of course, thanks Junyan to organize everything, organize this so amazing meetings. So my talk will be, I think this is some of our preliminary results, and the results are very straightforward at this stage because these are preliminary, okay? But first, I have to thank to Wei Hua, who trained the deep learning models, and Hao Xuan spent a lot of time for evaluate the model, and they work closely with each other to try to improve the hyperparameters in the deep learning model. And also, thanks Yong-Yun for rerun all the typhoon cases in 2024 so that we can do some statistical assessment of the AI model performance. So yeah, there are a lot of data-driven weather prediction models be published in the recent, since 2022, I think, so in the recent 3 years. But from 2022 to in the middle of 2023, I think everyone focused on the global deterministic data-driven prediction models, including the Penguin Weather, NVIDIA's ForecastNet and ForecastNet 2, Google's GraphCast, and even that European Center also developed their own AI model called AIFS. And after the emergence of the global deterministic AI models, new models pump out, and these models are targeting the global ensemble DWP forecast, so including the new version 3, the version 3 of ForecastNet from NVIDIA, Google's GenCast, or European Center's AIFS ensemble version. But today I'm talking more about the data-driven limited area model. So this kind of model, maybe you have heard about the neural land, which predict the Nordic domain in Northern Europe, and also the NVIDIA Stormcast, which is trained by the HER data and can predict the severe storm in the coldness domain. So in Taiwan, we are trying to developing our data-driven limited area mesoscale model around Taiwan, and we also try to develop a Lagrangian limited area transformer model, which is a TC following model, and we want to learn something before we really step forward to do high resolution AI learning. So why we need a limited area model? This is a good example. So this figure shows the track error verification, and they are European Center IFS and the other 3 AI models. And we did see that the GraphCast some of the AI model can have better track forecast compared to the numerical model. However, if we compare the AI model rainfall outputs, this is the rainfall prediction from Fuxi and the GraphCast. These 2 are AI models. And this is the ERA5, which is the training target of this AI model. This is the observation from Taiwanese radar network. And these 2 are from numerical models. This is the European Center model, and this is the WRF model at Central Weather Administration. So you can see that even though the DWP model learns from the ERA5 data, it still generates a much smoother rain pattern compared to their training data set. And of course, due to their limitation of horizontal resolution, AI model cannot representing all these rainfall detailed, which is essential for the wind and rain forecast during the typhoon period. So what we are thinking about, if we still use the ERA 5 data for training, but we only learn the specific weather system like a typhoon, can we get a better prediction than a global AI models? Because a global DWP model needs to learn all the features across the globe. So there must be a lot of compromisations, particularly for the smaller scale and local severe weather. So this presentation, we will talk about that we developed a TC following data-driven model, and which is still trained by the ERA 5 data. So it is not a high-resolution model, but it is a good starting point because we can know if we only focus on a specific weather system, can we learn better? And if we want to have a limited area model, how can we exchange the lateral boundary condition? So this is our first research question. Can AI learn better than global DWP when focusing on specific weather system? And second question is that because the LLath domain is designed to become a moving nesting DWP, so can we predict the coordinate motion, that is the CX, CY? And in this special case, the coordinate motion is also the TC motion. And the third, how can we facilitate the interaction between a limited area model and a global data-driven model? And I will show that we can do that in either a one-way or two-way interaction manners. And research question 3 is we also start to assess the physical process and try to understand to what extent the AI can learn the processes which is critical to TC development. So about our model design and methodology, first we still use the ERA 5 data for train this model, and we simply crop the data with respect to the TC center in a 20-degree by 20-degree domain. So the spatial resolution is 0.25 degree and 3 hourly data, and we follow the most of the global DWP model. We choose these 13 vertical layers as our vertical layers, and we have 6 upper level variables and also some other single level variables. And know that in our one unique thing in our model is that we include the vertical motion into our model. This variable is typically excluded in the global data-driven model. And we also include the total precipitation or the sea surface temperature and the long wave radiation, also the incoming shortwave radiation to our model. So because we are developing the model by ourselves, we can try to include more variables that we think it could be important to the processes we are interested in. And also for our Lagrangian framework, the latitude and longitude become our input and output. So our model will predict the latitude and longitude at each time step. So that's why we can predict the coordinate motion And also we take the average, the domain average of the latitude and longitude as the new TC position. So we basically use this kind of swing transformer AI algorithms as the backbone of our deep learning model. And this swing transformer is used in the lat-long coordinator. And because some papers, some AI models are using unstructured, graded, or graph neural network, which is better for high latitude or solving the pole problem. Yeah, but for typhoon, most of typhoon is in subtropical and tropical areas, and so we think latitude longitude coordinate could be sufficient. Could be sufficient for this kind of problem. Okay, and once the LLAT model is optimized, once we've trained our model, how could we do the model inferencing? The idea is that we have all the variables at t equals 0, and we input all the variables into our AI model, and the AI model will output all the states of all variables at t equals t plus 1. And as I mentioned that LLAT.ty model predict the TC center. So now we can calculate the averaged longitude and latitude to find the location, the location of our grid. So after we find the new location of our grid, we can get the boundary conditions from a NWP model or other data-driven global models, and we replace the boundary condition, and then we can use LLAT model to predict the variable state at t equals t plus 2. And also, our model can employ either one-way or two-way interaction with global DWP models. So how can we do that? If we use the one-way interaction setup, we simply replace the variables from the 8 pixels around our domain, only 8 pixels around our domain, which is like 100 kilometer scale. So we replace these values with the values in the ForecastNet version 2 variables. On the other hand, if we are doing a two-way interaction, we also replacing the ForecastNet 2 fields with those from the LLAT.ty. So this figures only shows a single level, but actually we replace the variable for overcall levels. And also when doing the two-way interaction, we only stuff a circular region back to the global DWP model. Otherwise, there will be like a wave number for a symmetry structure and causing a lot of issues. So that is our methodology. So then we do the reforecast for all 2024 typhoons. So for all 2024 typhoons, we have 26 systems has a lifetime maxima intensity larger than 65 knots, and we only do the reforecast at 00Z and 12Z. So we have a total of 319 initial conditions. And for each initial condition, we do a 132-hour reforecast. And for evaluation, we use the JTWC best track and the ERA 5 as our ground truth. Yeah, so the animation shows that this is for TC count rate, and we have several different setups. And for this time, you can see that the best track is the black line here. And first, if we use the ERA 5 data as our boundary condition, we get the pink line. So this is that there is no forecast error from your global model because we just use the observation, the ERA 5 as our boundary condition. And what we do forecast net 2 free run. So this is the prediction, and you only have a global data driven model. You can only get this yellow line. So there is a large track error. Okay, and the orange line indicates that we use the LLAT model, but only use the one-way interaction configuration with the forecast net 2. So we use the forecast net version 2 boundary prediction as the boundary condition, but the prediction from the LLAT model didn't feed back into the forecast net 2, and we get the orange line. And the two blue lines shows the forecast net 2 prediction and LLAT 2 prediction with the two-way interaction between these two models. So for the light and the light blue and the blue line, you can see that the TC center is collocated with each other. So this is some snapshot. So the same run, and this is at the lead time of 120 hours. So this is the surface wind from the ERA 5 data. This is from our LLAT model, and this is from the forecastNet version 2. So you see that because of forecastNet version 2 needs to take care of the features around our globe. So it seems has some difficulty to represent the strong wind associated with the tropical cycle. Even that we know the ERA 5 wind is underestimated if you compare to observation. Yeah, but if your model has to learn more about all the physical processes around the globe, it is very hard to represent what already shown in the ERA 5 data. And also the forecastNet version 2 cannot predict the rainfall and the precipitation, and this is the LLAT model's precipitation total rainfall predicted by the LLAT.ty model. So we can also examine the 850 millibar vorticity, and also the vertical motion at 700 millibar. And we can see that for the LLAT.ty model, it's not so bad, and it also have some signal of the vorticity associated with the terrain flow interaction. Of course, the magnitude is much smaller compared to the ERA 5 data. And I believe that in real world, this amplitude is even higher. Yeah. But at least we see some improvement compared to the forecastNet version 2. And this is for vertical motions. And also, this is for the cross-section, the same simulation. And the first row is the ERA 5. The second row is our LLAT model. The third row is the ForecastNet 2. Don't move. Right? Okay. Anyway, I want to stop that. Okay. So basically, you can see that if we train our model and force our model only focus on typhoons, we have a better ability to capture some fine-scale features. This is the wind core, this is vorticity, and this is the wind speed. And we can really generate more features compared to the global AI model. And we also do the track error verifications. So the yellow line is the ForecastNet version 2 model. So after 120 hours, the mean track errors is like 650 kilometers. Okay, and if we have a perfect lateral boundary condition, a very good lateral boundary condition from the ERA 5, we can reduce our track error to like 200 kilometers. However, we cannot get this peak line for operation because this is from the ERA 5 from the reanalysis data. So, but if we coupled our LLAT model and the ForecastNet version to the global DWP model, we can somehow improve the TC track forecast a little bit. And why we can improve our TC forecast, especially at this larger lead time, if we examine the error distribution of the ForecastNet version 2, we see that actually there are a lot of samples with very large track errors. So it sometimes happens because the ForecastNet predict the TC, which is a 2-week, or just predict the tropical cyclone dissipate. So after the TC dissipate, our tracker stayed at the same place. But if there is a real TCs, so the real TCs moves away and the error becomes larger and large. So this difference can be partly explained by that the pressure error, or maybe you can say the intensity, but you know, because in our verification we want to verify the maximum sustained wind of TC is very hard. So here we only compare the minimum pressure. So if we look at the minimum pressure error of these different configurations for TCs for weak systems, so which the minimum sea level pressure is larger than 950 millibar hectopascal, and we see that our models with the LLAT.TY has no pressure error bias for these weak storms. However, there is a significant bias between the ForecastNet version 2 model and the ERA 5 data. And if we look at stronger storms which has a lower minimum sea level pressure, the bias shown by these yellow bars, the ForecastNet model, is even larger. So let me make a quick summary here. So we train this LLAT model, and this model learns the feature evolution in Lagrangian coordinate systems. So we can do this TC following prediction. And we also predict the coordinate motion, which is also the TC motion. And also, our LLAT-TY model can operate with a global DWP model, such as the NVIDIA Forecast NEC2, via a two-way interaction for exchange lateral boundary conditions. And therefore, it could be a good intermediate model to bridge different kinds of global DW systems. And also, it can improve in the TC track forecasts. But why this AI model can do better is a crucial problem. So we also use this LLAT.TY model, try to conduct some idealized experiments, and we want to assess to what extent the LLAT model can learn a physical process. The key point here is that we want to identify the limitation in the LLAT.TY models so that we may have a chance to improve this model in the future. So today I will only show a few set of idealized experiments. The first set is that if we compare our control model, experiment A1 and experiment A2, this free model has a fixed location. So as I mentioned that we can calculate the new latitude and longitude at each time step, right? But if we just relocate the grid to the initial point, so we can do a fixed location simulation. And what we only change is the SST. So for these free experiments, we have SST of 299, 296, and 302K. And also we have another set of experiments. This set of experiments examine the influence from different background rotation. So still, the TC doesn't move in these simulations, but the initial latitude were changed. So the A2 is at 15 degrees north, the B1 is at 25 degrees north, and the B2 is at 35 degrees north. And all these three experiments has the same SST of 219K. And we also have another set we call experiment C to examine the beta drift and the TC motion. So for these idealized experiments, we simply choose the time and we calculate the azimuthal mean of all variable to get an initial vortex structure. And also we remove the length from our domain. So we set the landmass to 0, which means everywhere is there is ocean everywhere. But still, the forcing of solar radiation still inside our domain. So we will have a stronger solar incoming shortwave radiation during the daytime, and there is no shortwave radiation during the nighttime. Okay, so there is, and also I think this model can feel the background rotation, and which is more like on the beta plane. So let's see our results. This is the results from experiment A1. The SST is very low. It's only 200 and it's like 23 degrees Celsius. And this is 26 degrees Celsius. This is 29 degrees Celsius. So for these two rounds, we think it is reasonable. And if you have a 29 degrees Celsius SST, the TC is stronger and also produce more rainfall. For this one, first we think that it is kind of reasonable because we have less moisture and the TC is weaker. And then I thought, no, the SST is only 23 degrees Celsius. There should not be a tropical cyclone, right? So we do another experiment, A1 star. And the A1 star is that we also reset our SST to 23 degrees Celsius at every time step. And this is our result. And this result is more reasonable, right? So this is with 29 degrees, 29 degree, 26 degree, and 23 degree. And this one is our original 23. This one is with a 23 degree initial condition. So what happened in this run? We further examine the SST evolution for 24 hours, 72 hours, and 100 hours. So if we only change the SST to the initial 23 degree value, we notice that for experiment A1, the model will generate a higher SST by itself, because for most of our training data set, we only cropped the TCs, so the SST is typically very high. And our model feel 23 is some unrealistic value for SST. So it will generate a higher SST by themselves. So this reason.
Is this wrong with global models? No, this is standalone.
Yeah, it is standalone.
It's curious that the square things.
Oh, because this is the after we replace the boundary, and we make one more step. So you see there is
even there's no global link.
Yeah, there is we only replace the boundary, but the model is unstable. It will generate increasing SST by itself. Yeah.
Also, why is the asymmetry, the east and west SST asymmetry?
I don't know. We have to look at that. But anyway, it is something wrong in the model, right? So basically, this experiment indicate that we have to do more work and try to handle our lower boundary in a better way. But we don't have this kind of issue in our reforecast, because when we are doing the reforecast, we change the SST.
It's updated.
Yeah, it's updated. But if you don't update the SST, there is no reasonable physical process to handle this kind of things in the AI model. Yeah, so this is one limitation we found. And I believe we haven't examined the radiation forcing at the top of the boundary, but I believe there must be some issues at the top of the boundary. Yeah. And this is the second experiment, and this one is more straightforward. If we locate the TCs at different latitude, we see that the TCs will favor expansion in the higher latitude because the F is larger and you get more Earth angular momentum import to the tropical cyclone. Yeah. And how about the simulation C1 to C4? So these two simulations is not, we don't fix the location. So we have a quiescent background initial state. Only there is a vortex. So basically the vortex is drifted by the beta dryer. So actually we want to examine the beta drifting in our idealized model and see if the AI model can learn this physical process. So for C1 and C3, we have a larger initial vortex like this. And for C2 and C4, we have a smaller initial vortex. So first, we can look at C1 and C2. So this is the initial condition. There is no background flow, and we can examine the asymmetric wind or our stream function, the total stream function, symmetric stream function, and the asymmetric stream function. And this is 27 hours later. So we can clearly see that we have a beta dryer. So it is very good for our experiment C1. And this C1 is really drifted by, the TC is drifted by the beta dryer. And for experiment C2, we have a much smaller vortex size. So the beta dryer is much weaker and the TC moves slower. So it is also reasonable. But what happened in C3? Why a TC in the higher latitude move toward the northeast based on the beta dryer? So we examine the asymmetric wind at each layer. And we also calculate the mean flow at different radius. So green is 300 kilometer radius. This is pink, I think pink or red. This is 500 kilometer radius, and the purple is 800 kilometer radius, and at different vertical levels. So for this one, we see that it seems there is some westerly flow generated in the domain. So it is somehow weird. And why this westerly flow is generated in this domain is something we need to further examine in the future. So again, this is from the result from C1. This is from C3. So the difference between these two models is that the TC is relocated to a higher latitude. So this experiment show another weird thing in our AI model. We have to do more. We actually, it is our ongoing work. We see that if there is no vortex, there is a temperature gradient formed in our model, in our domain. Of course, maybe because we still have shock wave heating in our model, but I'm not sure that is everything. But anyway, we see if our model is initialized at a higher latitude, it generates a weird westerly flow.
Is that not just because it's trained and the real cases that's an expected correlation with latitude, that there's stronger westerly flow in a baroclinic zone, maybe?
Possible, yeah, but if it is true, then it is not we really want, right? Yeah. Because we want the AI model to really learn some physics and not just do the analog. Yeah. So
But it's always difficult to try to separate the typhoon versus the environment.
And the training.
Training.
Because it'll probably create its own next tropical transition, right?
Yeah.
Eventually. If
Actually,
it's based on latitude.
And all of our training data may have stronger westerly wind in that area.
Yeah.
Yeah. But
I think that's probably because you focus on that there's some environmental background there. You learn it together.
yeah, so my bottom line is that although this AI model seems could be efficient in operational forecasting, we need to do more physical process-based evaluation, and maybe based on conducting idealized experiment to really examine what physical process is learned by the AI and what is not. And we need to identify the model's limitation, and maybe in this way we can keep improving it and have more and make it more trustworthy in the future. Yeah. So that's all I have today. Thanks.
I think, this is how ongoing work. One of the points, I guess, is if you're using the almost perfect, and your truth is error factory. So one thing it shows is that you can have an effect. You can receive the benign effect of the boundary from the lateral side. And then the second thing seems to me also significant is that it allows you to have a consistent two-way interaction, which I think in the NTUxOUxP model, in the numerical model, it's very difficult unless you're within the WRF, right? But if you have a WRF and a global model, so that gives a very nice foundation. But then from there, then try to find out the deficiencies of the model and see what can we do. But so when you're doing this, the two-way interaction, is that the same in the low latitude versus the one in the high latitude?
Yeah.
In the two-way, they're both consistent.
Sorry, so the two-way, what's the difference? Because one way I can understand from the boundary layer to your training model. How about two-way?
Okay. Typically in NWP models, we cannot do two-way interaction between two models because we typically download the NCEP forecast from the website, right?
Yes.
But for the data-driven model, it is very cheap. So we can run the global data-driven prediction model by ourselves.
Oh, so you actually you have two numerical models.
Two AI models.
Driven the models.
Yeah.
Global is the one you're small. It's gonna remind me. Right now, since I'm come from the Silicon Valley area, so nowadays AI is the term, but the most popular term is called AI agent. So neuro study actually that means kind of come up with words AI agent, just specifically looking at kind of a function. So you are not looking for overall big, like we are training the global machine learning driven the global time model or weather forecast model. You are focused on the one type of the phenomena. So like right now you have the typhoon tracking. So you are just targeting the typhoon and doing the tracking, and we are called agents. So you are only doing one thing. You are not doing the multiple things together. So before our concept, we say, we are located in Taiwan. So we are trying to train the models to capture all phenomena in Taiwan. That means the model have to do, even the machine learning model have to learn how to capture those phenomena at one time. But the next information or the mechanism actually comes from different. For the mechanism, we are targeting the one phenomenon. We ask the model to train this phenomenon only. So I think that we can, like Taiwan, so we have a certain 3 or 4 typical weather phenomena, like the rainy season, so also winters, frontal break, winter break. So we can only take just train the model doing the one thing and not doing the multiple things. Maybe they will become smarter then the computational cost actually also will be lower.
Yeah.
So that's why nowadays the people will talk about AI, especially industry. They are not just saying how great the model can do multiple things. Actually, they just want to do the one thing and do the things better. So like kind of AI agents are becoming quite trendy kind of words in the Silicon Valley now.
So the where maybe Bohu can explain more. If you look at this, once you're interested in the limited area model, so the CODIP from NVIDIA, the global part of the mean part is, I mean, all these great AIFS or whatever, right? But then below the 28 kilometers, certainly you have some numerical simulations from the RWALK, but then they try to use that in the diffusion model. So then in this way, training diffusion model is very expensive. So I think in the CODIP, they only have 13 vertical levels. But now we're thinking is that we want to have more vertical levels to, in the future, maybe have better radiation or other things. So we increase the vertical resolution, but we cannot under 28 kilometers. So we want to have something with a more target based the storm column for the diffusion model with high resolution. But maybe some 28 kilometer to 4 kilometer that region, we are hoping to have training the regional model. So one of the things, a must would be you can have a total benign effect from the large scale boundaries. And hopefully if they can be consistent two-way interactions. That to me, that's the way I see how this. Maybe both can explain it better than that.
I really appreciate Xianghe's comments, because even now training the foundation model is too expensive and only limited for those huge companies. So I think in Silicon Valley, small group want to find something new, so they start to think about maybe I can only handle one specific task, but I can do that task very well. So that is the idea of AI agent, right?
Saying there too long. I feel like these days I come back to visit here. So we are really focused on the fundamentals research, looking at some of the dynamic, the phenomena, the kind of theories here. On the industry side, I think they are looking forward to product. So the product ends actually says what you can provide the best, and then you will not be different. So actually, for us, we definitely won't be able to simulate everything, to train everything as well. But we can come out of something good, and then it will become our product, and then they can sell this kind of product. So that's how the people's concept. You see the those startup company, you will feel like okay, actually they only know to do one thing. But they are just quickly kind of launch the ideas, and they say, oh, we are looking for the investors and how many people come out to investors and do the things. Yeah. So actually, you look at the details, they only know the one thing, and then they will come out to say, okay, we can do these things better.
Yeah, I think that's thanks, Xianghe, very good comment. It's also it is I debated myself and I talk to other people, is that so long you just get the two-dimensional fidelity graph, right? All you care is about precipitation. You try real hard to then get the right precipitation, but that's a 2D. Right? But we're just hoping that we want to have a 3D fidelity. So in a way, like free round model, I don't care about the microphysics, so long as I tune the model get the right range, right? But probably, as being an academic study, we hope still that. But to me, I feel it's important to have this kind of things that Because I know there's an interesting thing like Jim is starting and a lot of these new observations coming, right? You want to have something at the proper base, more resolution, right? More variables in the ice species. But if you're just looking at the product in 2 dimensions, I think from operational point of view, sometimes it's okay. But we are hoping, maybe I myself a little bit ambitious, I was hoping that we can do the operational one thing, but also set up some simple frame that we can easily do this kind of denial type of experiment. In the end-to-end, but in the between we can play around with it. And from there, maybe help us to do more numerical experiment, a guide to do. I'm not saying we just do this would be now, but that.
Don't think me wrong. Actually, I'm saying that because we definitely have that kind of knowledge. Because you look at those industry, those people that are working in the NVIDIA, so even in the kind of global models, those machine learning weather forecaster training group, you did a background on computer science background. And for us, we know how to train this model. We know which kind of major parameters that we should train. We are not looking for kind of 10 parameters that try to train it and come out a good idea, good result. But we are, especially for us, we have a really limited resource. So we can targeting those that, okay, those are 10 like a global models, the 10 variables that we need to know. It's okay, 3 or 4 key parameters that we can kind of looking for the kind of type of checking. We can do it better. And for the kind of like the frontals, the reinforced, and we know that actually they will be looking for another 4 different variables and can get it better. That's the kind of basic knowledge we have. This is not that we are just have a bunch of the machines and we can train the models limited state and just come out with a good idea and then also tune the model. I think that's looking at the base, especially really nice talk of all the speakers. We have the really good fundamentals, the knowledge, and we have the tools here. Unfortunately, actually our resources pretty limited, and how can we just build out our knowledge on this limited resource that we can come out with pretty good results. That's how I feel like that both was research actually have these 2 combinations together.
Yeah. You just in the real life you have to balance. For example, my way of saying, you have to balance yourself with the operational need. Maybe all you need is a 2-dimensional fidelity. But on the other hand, you want to have a better value structure, 3-dimensional fidelity, but you cannot go infinite. So that's somewhere I think actually the domain knowledge of the science is so important to guide us. You know, I do not want to simply argue. I want to have 60 levels and 20 ice species, but even computers have 20. I think that's somewhere, and I think that's the essence when we have in the CSU talking to Christine and Michael. This is actually there's more, the things more involved in the science details. But I think basically we simplify. We say we want to have 3D fidelities. It's something we in the NCAR we hear. I like his talk very much. The person and
you mean Will Champ?
Yeah,
Will Champ.
Yeah. He did a very interesting study. He ran the model, climate model, and then he compared that to the error path, and learn how to fix the error. And then he using the fixing things to, we go to the real climate, and he was presenting a very nice NGO. So it's in a way the people they used to, call it the MOS, model study, but this kind of thing is really happening in the real because model keeps on changing and data quality. But I think this is what Chapman seems to. But most striking me is that apparently all the fixing is in the boundary layer. He's not fixing everywhere, go everywhere to go fixing the model. He's really concentrated. He has a target, and he's fixing the boundary layer. So I think this eventually we're hoping to have a better foundation, but I myself believe it should be science-based. Otherwise, it's a wild goose.
Is there any stage that already has, or do you think about? I know we talked a little bit about kind of energy conservation, and of course, like for like a climate modeling context, that's important. Maybe less so for weather scale, but when you were showing the vertical structure, that came to mind. Of course, in the training data, there's mass wind balance that provides mass wind balance in the product. But do you imagine it being helpful to incorporate a stage, sort of an adjustment that is trying to balance things, or? I know that's been one kind of subfield, one discussion in the AI community is like imposing physical constraint.
Yeah, but I actually we have cooperated with some other computer science guide, and we have some discussion about this. If we just add some physical constraint to our loss function, we still not guarantee that the AI model will output everything follow that physical constraint, because during the optimization process, the goal is to minimize the loss, but not make your output 100% follow your rules, right? So they suggest that what we can do is, because all of these AI models are doing in the auto-regressive manner, that means we take our last output as our new input and again and again and again. So yeah, so we are thinking about maybe what we can do is that we can add a module, and before each time we input our previous output into the model for the prediction for the new time step, we can correct the input value. For example, correct the energy spectrum of every variable. So we are thinking about that. So maybe at this stage, we can also ask the model to obey the balance dynamic in some larger scale. But still, we have all the smaller scale variability inside. So, but we just start to thinking of this. Yeah, but directly add the physical constraint into the model. We've talked about it, but we don't really like it because as I said, even we add the physical constraint into our loss function, that doesn't guarantee the model will really output many out something which obey the equation. Yeah, because because we are not doing implicit calculation that what we are doing in numerical weather prediction models. Yeah.
I try to think of this as a way in the whole time. Error is accumulating in the system, right? So we cannot just with a long-term integration. So our core Jacobi is a way to try to put a constraint on entropy and energy. But actually, it allows you to have a long-term integration, but still, again, not total accurate.
Yeah.
But it just controls. So so maybe I'm thinking more like, I do like the way constraint, except I do not know, because we're not talking about large scale. And I'm so concerned about everything. Because I look at some of this, the large scale, and the energy spectrum in the end is just totally not right. So I don't know, but I personally, I like the idea to adding some loss function. But I think that's been, to me, I would think that this is being done by, traditional that just doing more to do.
Yeah.
With this mesoscale thing.
Yeah. Well, and I mean, it's clear that it is implicitly there, like the development of the baroclinic zone. You mentioned this temperature gradient associated with developing westerly wind. That sounds to be something that's kind of a geostrophic adjustment. I mean, it's an completely artificial drift, but they're happening in a balanced way. Maybe, if that's what's going on.
So I think what we are do next is we will examine the temperature gradient and the wind gradient and see if there is a thermal wind balance. I think if there is a thermal wind balance, we will feel better. And the other thing I can play with is to examine the relation of the incoming solar radiation and the temperature gradient. Because we have a variable which is the incoming solar radiation. So we have something to play with. But I don't know. Maybe if we turn on if we turn off the solar radiation, we still see there is a meridional temperature gradient. So that may indicate our model is wrong in some way.
I mean, very naively, my head goes towards the idea that it's because it's getting into the more baroclinic higher latitudes more than due to the radiation. But yeah, I'm interested to see.
Okay.
I'm also curious, I know it's not the direction that's planned, and I guess it's also not an affordable experiment, but I'm also just curious what happens in stripping away variables that you're using, that you're incorporating. Which ones account for the biggest loss in fidelity of what you currently have versus which ones could be, small incremental improvements if you include or don't include them, because I guess several of them at least are coupled and interrelated, but I don't have the experience in doing that kind of a training and experiment to know how important it is to include all the different things.
Yeah, it is a good suggestion. Maybe I will think about it. At least I think we can play with something like the diurnal cycle short wave and long wave, or the SST. So we can remove some variables which is highly related to the forcing to our domain. But so that we don't need to do this kind of experiment for UV, TQ, Z, and W. But we can play with our radiative forcing, long wave, short wave, SST. Thanks. That could be something good to think in the future.
Because then also, if it's important to build more vertical layers, part of maybe compromise is having less variables.
I was also wondering if the learning of this maybe SST is kind of important because if you're a slow drifter, you're faster one, maybe the upweighting and type of thing for certain feedback.
Okay, there is no SST coding in this model. We've examined it. And but it is reasonable because there is also no SST coding in the ERA 5 data.
That's really impressive, though.
Okay. So.
Okay. Many thanks to both who wrote about the conversations today, and I think we had a really, really good time. And thanks for all the speakers, and also thanks Dr. Xiang He. Just get all the and providing a lot of comments.
Thank you, everyone.
Thank you. Thank you all.
We've come a long way but I really enjoyed
So much fun.
Yeah.
So much fun.
All the talks were fantastic and really great discussions. I found the work really nice and inspiring, and so I'm really grateful for the chance to come and be part of this conversation.
Next time, bring your students here.
Yeah.
Next time, yeah.
Yeah, I think that's the promise of the NTUOU for Penn State. We should do that. It's good.
We have a good excuse to do this again because John cannot made it this time.
Definitely this time.
Yeah, so for John.
Next time.